Okay, from this video, let's start at chapter 6, exponential and logarithmic functions. Okay, so first, composite functions. When we have several functions, for example, we have two functions, we can do addition, we can do subtraction, we can do multiplication, and we can also do division when the denominator is not equal to 0. So for all these arithmetic constructions, we have one requirement, the domain. The domain of them, except the quotient. Quotient require something special, additional, not special, additional. The domain of them is equal to the domain of f intersect the domain of g. So basically, if fg have the same domain, then the domain of these constructions is the same. But sometimes we have another type of stuff. For example, this is about addition, subtraction, multiplication, division, and sometimes we want to do something like this. So we have a set, and we have a second set. That's a function f. F is like the first step operation. After the first step operation, we start from the result, we get a second step. Okay, so this is the second step operation. And by this operation, we can see that the domain of G is totally different from the domain of F. Because the domain of G is more or less the range of F. So this operation is the operation we call composite function. And it is totally different from those four operations. Okay, so let's see the definition. So given two functions, f and g, the composite function denoted by f circle g, f composed with g. Okay, read as f composed with g is defined by f composed with g of x is equal to f g of x. Well, here let's change the order. Change the order. Here in this definition, they do g first, f second. Okay, so basically what it means, you have an x here, you apply function g. G maps x to certain value, we call it g of x. And then f starts from g of x and map it to f of g of x. And this whole operation from x to f of g of x is called f composed with g. Okay, it's called f composed with g. Now let's talk about the domain. The domain of F composed with G is the set, the domain is here, not the middle, domain is here, is a set of all numbers x in the domain of G first it has to come from this set, and such that G of x is in the domain of F such that this result should be in the domain of a second function. Okay, so first x comes from here. Second, G of x in the proper domain of F. So this gave us the domain of F composed with G. It have to make two functions well defined. Okay. So for example, your x is like this, and the domain, the range of G is here. The domain of F is here. And this part comes from where? Comes from here. And the top part is mapped to this unshadowed region, and then this shadowed region is also mapped to this shadowed region. So what is the domain? Domain is just this piece, because this piece is in the domain of G and it is mapped to the domain of F and it goes to this place. So this is a range of F composed with G. Okay? Okay, let's see the example. Suppose that fx is equal to 2x squared minus 3, and g of x is equal to 4x. Find a f composed with g of 1. F composed with g of 1, let's check. It's by definition f of g of 1. G of 1, read here, g of 1. G of 1 is 4 times 1 is 4. So you evaluate g of 1, you get 4. And then f of 4. F of 4 is 2 times 4 squared minus 3. 2 times 16 is 32. 32 minus 3 is 29. Right? So this value comes from here, and this expression comes from here. So in different steps, you follow different definition. And G composed with F of 1. Let's check this one. By definition, it's a G of F of 1. So you always apply the closer function first. You apply the closer function first. So f of 1, check here, f of 1 is 2 times 1 minus 3 is g of negative 1, right? And g of negative 1 is negative 4. G of negative 1 is negative. So from here you can see that f compose g, g compose f, They're totally different. They are not commutative. You cannot switch them. Second, let's try f composed with f. Evaluate at -2. F of -2, f of -2 is f of 2 times 4 minus 3. It's f of 5. F of 5 is put here. So it's a 5 squared is 25 times 2 is 50. 50 minus 3. 47. Right. Another one. G composed with G evaluated at -1. So it's G of -1. G of -1 is -4. G of -4 is -16. -4 times 4, -16. So this is the evaluation. You don't have any tricky method. Just do it step by step. You have to follow the step. So this the direct evaluation with a concrete number. Okay. And second, suppose that fx x squared plus 3x minus 1 gx 2x plus 3. First, let's study the composite function f composed with g. F composed with g, let's just check the expression formula. F of g of x. gx 2x plus 3, so f of 2x plus 3. And f of 2x plus 3, it means whenever you have, in the original formula, whenever you have x, you're going to use 2x plus 3. Okay, so it becomes 2x plus 3 squared plus 3 times 2x plus 3 and minus 1. So whenever you have x, you're going to write 2x plus 3. Okay, now we can expand it. Yeah, we can expand it. It's 4x squared plus 12x plus 9 and plus 6x and plus 9 minus 1. So it's 4x squared, 18x, 17. 18x, 17, yeah. And you can see that what is the domain of this composite function? The domain of G is a set of the domain of G is a set of all real numbers. The domain of F is also the set of all real numbers. We're talking about polynomials. So they're both the set of all real numbers. So whatever image G has, it is always in the domain of F. So the domain of F composed G is equal to negative infinite to past infinite also. So you can just choose whatever x here. It is always mapped to infinity, negative infinite, past infinite, and it always well defined for F. Okay, so this is the first thing. Second, let's check G composed with F. G composed with f by definition is G of f of x. F of x, where is f of x? X squared plus 3x minus 1. So it's G of x squared plus 3x minus 1. And G of x is 2x plus 3. So you get whatever inside times 2 and plus 3. So it's 2x squared plus 6x and minus 2 plus 3. So it's a 2x squared plus 6x and plus 1. It's also a polynomial. And because it is a composite function of two polynomials, f has domain the set of all real numbers. G has domain the set of all real numbers. So the domain of G composed with f is also from negative infinity to positive infinity. But those two functions are quite different. Okay? Okay, let's see next. Find the domain of f composed with G if fx is equal to 1 plus x plus 2, 1 over x plus 2, and G of x is equal to 4 over x minus 1. 4 over x minus 1. Okay, so what we need in order to find the domain, first we need the domain of G. The domain of G of x inside is equal to the set of all real numbers, so that x is not equal to negative 1, is not equal to 1. When x is equal to 1, the denominator is 0, so that's not allowed. Okay, so this is domain of G. And second, we need the image in the domain of f. The domain of f is a set of all real numbers, so that x is not equal to negative 2. X is not equal to negative 2. So it means G of x, G is inside the domain of f, so G of x is not equal to negative 2. G of x cannot be equal to negative 2. So we are going to figure out what is the corresponding value for x. Okay? In order to exclude this number, let's first determine it. Gx is negative 2. What is Gx? Gx is here. So 4 over x minus 1 is equal to negative 2. We multiply two sides by x minus 1. So it's 4 is equal to negative 2 times x minus 1. So 4 is equal to negative 2x and plus 2. Move negative 2x to the left side, 4 to the right side. 2x is equal to 2 minus 4. 2x is equal to negative 2. X is negative 1. Okay, so x is negative 1. So the domain of f composed G is the set of all real number x except x cannot be 1. It comes from the domain of G, and x cannot be negative 1. It comes from the range of G cannot be negative 2. Okay, so the range of G cannot be equal to negative 2. We have to exclude this solution. So this is how we find the domain of a composite function. Satisfy the domain of G, it also satisfies that the range of G is inside the domain of f. Okay? Let's see another example. Suppose that fx is 1 over x plus 2 and gx is 4 over x minus 1. Same function. And find a f compose g. Okay. We have a, we also have b. Let's see. We just computed this is the same thing. So the domain of f compose g is the set of all real numbers so that x is not equal to 1 and x is not equal to negative 1. This is the domain. Now let's try to really find the formula. That problem, we only need to find the domain. Here we need to find the formula. So it's f compose g of x. So what's this? It's a f of 4 over x minus 1. 4 over x minus 1, right? And fx is here. So it is equal to 1 over 4 over x minus 1 and plus 2. Just replace x by this complex formula. And then we just try to simplify it. We simplify the denominator. It's 4 plus 2 times x minus 1. You flip this x minus 1 to the numerator. You get 4 plus 2x minus 2. So x minus 1 over 2 plus 2x. 2 plus 2x. Okay, so this is the composite function f composed with g, and with the domain like this. Okay, so this is the first one. B. Find the composite function f composed with f. First, let's try to just directly compute the formula, and then we discuss the domain. So f composed with f of x. Okay. fx is 1 over x plus 2. So it becomes f of 1 over x plus 2. You have x, you just replace x by 1 over x plus 2 and plus 2. Right? So this x, you write 1 over x plus 2. Other numbers, you just copy. And we simplify it. And we flip the denominator to the numerator. It's 2x plus 3. You see, 5. So 2 times x, 2x. 2 times 2 is 4. 4 plus 1 is 5. Okay, so this is a formula. And now let's look for the domain of f. The domain of f composed with f. So first, the domain of f is a set of all real numbers except x cannot be equal to negative 2. That comes from the domain of f. And second, since we're going to compose f with f, so the fx cannot be equal to negative 2. So this value cannot be equal to negative 2. Okay, so in order to exclude this value, the corresponding x value, let's try to compute what is a corresponding value. So we put 1 over x plus 2 equal to negative 2, and this is 1 equal to negative 2 x plus 2. So 1 is negative 2x minus 4. So it's 2x is equal to negative 5. I move these two numbers, negative 2x to the left, 1 to the right. So x is equal to negative 5 over 2. So this is the corresponding solution for fx equal to negative 2. And we have to exclude it. We have to exclude it. So the domain of f is equal to the set of all real numbers except x is not equal to -2 and x is not equal to -5/2. So this is the domain. Okay? This one is the domain. Okay. Let's see more examples. If fx is equal to 3x minus 4 and g of x is 1 over 3x plus 4, 1 over 3 times x plus 4, show that f composed with g of x is equal to g composed with f of x is equal to x for every x in the domain of f composed with g and g composed with f. Okay, so let's try it. They ask you to show it. Actually, you just compute, right? Let's try f composed with g of x. It's f of g of x. G of x is 1 over 3 times x plus 4. And then we apply f. F means when you have x multiplied by 3. And then minus 4. 3 times 1/3 is 1, so it's x plus 4 minus 4 is x. So this is one part. This one is equal to x. And let's see another direction. G composed with f of x. It is g of f of x. Here's f of x. 3x minus 4. G of 3x minus 4. G of x is here. So it's a 1 over 3. Whenever you have x, you write 3x minus 4 and then plus 4. Minus 4 plus 4 cancelled, you have 3x. 3x times 1/3 is x. So g composed with f of x is equal to f composed with g of x is equal to x, because you just compute it. There's no proof, it's just computation directly. They are both polynomial. Both polynomial functions. The domain g composed with f is equal to the domain f composed with g composed with f, both negative infinity to positive infinity. They share the same domain. So this is an interesting pair. They share the same domain. F composed with g composed with f are equal to each other, and also they are equal to x. Okay. So what does this mean? This actually mean the following. You have the set of x. You have a set of y. You have x here then g applies x to g of x. Then f, you see, f applies a g of x to x. You see here, it's like the back and forth. You go move it back and move it back. You move it forward and you move it backward. Right? So here g maps x to g of x and f maps g of x to x. So from here to here and here back. So that's what it the graphical description of the computation. The graphical description. Okay. If you have those parts like f and g, you can do the composite operations, and sometimes you should be able to decompose a complex function into a composite the composite function of several functions. So let's check. Check example. Find functions f and g such that f composed with g is equal to h if h of x is equal to x squared plus 1 to 50th power. So how do we do it? Remember we mentioned what is a composite function. Composite function is like the steps between the sets. You apply the first operation, the first step, and you apply the second operation, second step. So here, if we study this function, we will figure out actually the first step we apply is this x squared plus 1. You whenever have input x, you apply this operation x squared plus 1. You find a value. After you get this value, you take the 50th power. Right? So the first step is this x squared plus 1. This is x squared plus 1. After you figure out this x squared plus 1, once you get this value, you compute the 50th power. Some value, take 50th power. Okay? So that's exactly what we, that's how we define this step function. The first step function, second step function. G and F. They are once you compose these two functions together, you will get H. Right? So it is equal to H of X. And this is the solution. This is a solution. Let's see more. Let's see more. For example, if you have square root x squared plus 1, how do you do that? You first compute x squared plus 1. Once you get the value, it takes the square root. So your g of x is going to be x squared plus 1. Your fx is going to be square root of x. Right? And f compose with g is equal to h. Of course, this composition is not this decomposition is not unique. When you have two parts, you compose them together. That is unique. But when you have a big part, when you decompose it, it's not normally it's not unique. We can do the following thing. We can also, like for example, we just define g1 of x as a x squared. And what is f? fx, we define it to be square root of x plus 1. Then what is f1? Then what is f1 compose g1 of x? It is f1 of x squared. And then you replace x by x squared, you will get square root of x squared plus 1. It is h. So this is also a decomposition. It is also decomposition. So you have two parts, you glue them together, unique. You have a one part, you try to cut it, chop it into several pieces. You can chop it from here, this point. You can chop it from this point. So normally it's not unique by logic. So that's why there's no standard. There's no unique solution, but there's a standard solution. At least for me, I consider this as a standard solution. But again, it's not unique. It's just my opinion. Okay. And another example. Let's see, for example, h of x is equal to opposite value of 2x squared plus 3. Then we will define, you see here, you basically, how do you find the g and f? You just see what is your first step of computation, what is your second step of computation. So first step of computation, you don't check the opposite value, you just compute 2x squared plus 3. And after you get it, you compute the opposite value function, right? That's the orders. So we will define g of x as 2x squared plus 3 and fx as opposite value of x. Once you figure out this value, you put opposite value. So f composed with g of x is equal to opposite value of f of 2x squared plus 3, and then you put absolute value, right? It is equal to h of x. So the decomposition is not extremely difficult. You just try to understand the steps in this complex computation. You will get the answer. Okay? So this is section 6.1. In the section 6.1, we just try to discuss the composite function. We have two parts. How do we compose them together to get a complex function? So you just get one step. You apply second step on one step based on the first step. That's a composite function. Or you can decompose a complex function into several simple steps. So that's two operations. And be careful, there's one special example. In this example, you see g maps x to gx, f maps gx to x. So it's like a back and forth operations. So we will study this type of composition a lot in the next few sections. Okay, so this is the section 6.1, the composite functions. Okay, we finished this video and we will continue another video. Thank you.